Now, let's take a look at some parametric tests, non-parametric tests, I mean. So the first non-parametric test that we're going to look into would be the runs test for randomness. The runs test evaluates the randomness of a series by observing and analyzing the number of runs it contains. When we say a run, it's the consecutive appearance of one or more observations that are similar. For example, this is what there are 3 runs in this sequence. It's W, M, and then W. Then there are 6 runs in this sequence, regardless whether it's just one or more similar. Now, the reason for this is because sometimes, even though it says it's random, it might not actually be random. And then, with that, since we would need randomness in one or more of our processes, that's the reason why we need to test whether the sequence is random or not. Because if it's not random and what you require is random, then something must be wrong with the machine or the process that we're checking at. So our null hypothesis for the runs tests is that the sequence is random, and the alternative hypothesis is that the sequence is not random. Let's have one example. So, a political activist claims to have randomly stopped persons at a street corner and asked them to sign his petition and give their age. During his first hour on the street, 30 people signed the document and gave their ages, and the order is as shown in the table below. At 0.05 level of significance, evaluate the randomness of the ages for the sequence of 30 respondents. Alright, so the order in which they sign it is horizontally given, so like that. So this should be encoded, and then we'll see whether it's really randomly or it was not randomly done. Alright, so we have now our tests here. So, our data here rather, so we have our data typed in. So now we're going to conduct a runs test using XLSTAT to determine whether this is actually a random sequence or not. Alright, so the first thing that we'll do is we go to non-parametric test. We go down to one sample runs test. There you go. So we select our data here. There you go. Then, since our data is quantitative, because that's age, we select it as quantitative. Then we just let the cut point as median. Then I would like again to have it on a separate sheet, column labels in. So we're testing for randomness. Now our significance level, let's just check. At 0.05, it says here, so 5% level of significance. Then we'll have exactly value. There you go. I will still have to like the descriptive statistics just to show. Then we click OK, and this is continue. So here you go. So just in case you would need, for example, the mean and the standard deviation of the data set, it's here. So we have here the p-value. There are 10 runs in the data set, but the expected runs is supposedly 16. And the p-value is kept with the exact method. Now we can see that 0.04 is lower than 0.05. So we already have this one. So from here, we can then write manually our, what do we call this? Our, steps for hypothesis test, because more or less it's the same. So the first thing, our first step is to declare our HO and our HA, which we already mentioned and XLSTAT already gave it. So the sequence or the data is random, while the HA is the data is not random. So this is already steps 2 and 3. So step 4 will simply get the p-value of 0.040 against the alpha of 0.05, which is obviously it's that. So therefore we have rejected HO, and the conclusion that we say now is that the data sorry, we first say, there you go. We first say that there is sufficient evidence to reject HO. Thus, the data is not random. So there you go. It's the same steps, just a different test done by a different and then done different. As simple as that. Number 2 will be left for you to solve. But I think the problem is incomplete. This is the batch, and then we have to use alpha is equal to 0.05. At 0.05 level of significance, test whether this batch is actually a random batch. And this is one example in manufacturing as to why we need randomness. So we leave this to you to figure out whether this is really random or not. Now, the next non-parametric test that we're going to do is the Wilcoxon sign rank test for one sample. So for one sample, the Wilcoxon sign rank method tests whether the sample could have been drawn from a population having the hypothesized value as its median, not mean. And this is the parametric counterpart of the one sample t-test. So no assumptions are made about the specific shape of the population except that it's supposed to be symmetric. And data are assumed to be continuous and of racial scale measurement. If not, then we can do an alternative technique called the sign test. So we'll first go in we'll just have Wilcoxon sign rank due to XLSTAT. So let's have an example. An environmental activist believes her community's drinking water contains at least the 40.0 parts per million ppm limit recommended by the health officials for a certain metal. In response to her claim, the health department samples and analyzes drinking water from a sample of 11 households in the community. The results are residual levels of this, and at 0.05 level of significance can be concluded the community's drinking water might equal or exceed the 40.0 ppm recommended limit. So, let's now go to our data set. Alright, so we now have our data type here. And this is what we had a while ago to determine whether this is our sample rather on our Kolmogorov-Smirnov test. So, for XLSTAT, it's usually better if we already have to declare our HO and HA. So with that, let's write already our step 1. Our HO, according to the problem, is that it might be equal or exceed the 40 ppm. So, whether the median is greater than or equal to the 40.0 ppm. While for HA, if the median is less than 40 ppm. Making this a one-tail, lower tail test. So now, we then go to non-parametric test, one sample Wilcoxon sign rank. So, okay, since we selected that I think for the Kolmogorov, that's why it's already selected there. So sheets, column labels. For the options, this is the reason why we already wrote our hypothesis, because we need it here. So it's already set, less than, there we go. Our theoretical median according to the problem is 40, so we write that. 40.0, significance level according to the problem is 5. There you go, and then we click OK and then continue. So it's bigger. Alright, so what we have here, we have our values here, your minimum and maximum, you have your mean standard deviation because it's quantitative. Now, what we have here is that this is our steps 2 and 3, and we now go to step 4. The p-value of 0.225 compared to the alpha of 0.05 is indeed bigger. Therefore, we conclude that there is no sufficient evidence to reject HO. Thus, we say that the median is indeed greater than or equal to 40 parts per million. So more or less, the steps of hypothesis test is the same. It's just a different test. So there you go. So the other example, this one here, will be left for you to answer on your own as an exercise. So a convenience store owner hypothesizes that the median number of snow cones she sells per day is 40. So using this data set, determine whether it's really 40 or not at 0.05 level of significance. So we just had the runs test for randomness and the Wilcoxon sign rank test for one sample.